So, where do numbers come from? I mean, it seems like a simple question, right? They're just there, kind of like rocks or trees. But what if I told you the story of numbers is actually this incredible drama, a tale of human invention, intense philosophical debate, and a crisis that shook the very foundations of logic itself? Okay, let's really get into this. What we're going to do is trace the evolution of that very idea. It's a journey that's going to take us from something as simple as counting on our fingers all the way to one of the most powerful and sophisticated concepts in all of mathematics, the continuum. Our story has to start with the most basic numbers of all, the integers. You know, the 1, 2, 3 that we use for counting. These numbers just feel fundamental, almost like they're woven into the fabric of the universe. And they grew out of the most basic human needs. Now, for literally thousands of years, humans just used numbers. They were a tool, like tally marks scratched on a bone. But the really deep question of what a number is, what are its actual logical properties, that wasn't seriously figured out until the 19th century. Just think about that for a second. There's this massive gap between just using numbers and truly understanding what they are.
This famous quote from the mathematician Leopold Kronecker, man, it gets right to the heart of a huge philosophical debate. Are numbers, like the integers, something we discovered? Were they just out there, waiting for us? Or are they a purely human invention? Kronecker, he was convinced the integers were divine, a given. Everything else, that was on us. That was our creation.
Look, if you're going to build this vast universe of mathematics, you need a solid foundation, a bedrock. For natural numbers, that bedrock came from something called Peano's axioms. These are just a few simple, almost obvious truths, like every number has a next number, a successor. They act as the fundamental rules of the game. And from just these basic rules, all the properties of counting and arithmetic could be logically proven. It made sure everything was built on solid ground. But, of course, the natural numbers weren't enough. As human problems got more and more complex, we needed new tools. So this next phase of the story, it wasn't really about discovering new numbers. It was about inventing them to solve very specific problems that the old numbers just couldn't handle. And so the great expansion began. We started with natural numbers, for counting stuff. But what about division or debt? For that, we had to invent rational and negative numbers. And then, to solve even deeper, trickier equations, we created the strange and powerful complex numbers. Every single step was a deliberate act of creation, and each one unlocked a whole new mathematical world. But here's the thing. The real story isn't what you might think. A lot of us are taught that negative numbers were invented for a simple problem, like, say, 5 minus 7. The reality? Nope. They actually came out of much more complex algebraic problems. And the same thing goes for complex numbers. They weren't just created to solve a simple equation like x squared plus 1 equals 0. They were actually the secret key needed to crack really difficult cubic equations. So with this expanding toolkit of numbers, mathematicians set their sights on a really grand goal: to perfectly describe the smooth, unbroken line of reality itself. They wanted to create a number system that had absolutely no gaps, no jumps, a perfect, seamless continuum. This system is what we now call the real numbers. The ambition here was huge, to create something so infinitely dense that it could match up with every single point on a geometric line. And this wasn't just some abstract game. It was absolutely essential for linking the pure world of math to the real-world modeling needed for physics and science. So how in the world do you build this perfectly smooth line? Well, mathematicians came up with some truly ingenious methods. One idea, called Dedekind cuts, was to imagine literally splitting the entire number line in two to perfectly define the number at that exact cut. Another was about zeroing in on a point with smaller and smaller intervals. But a third, and kind of surprising, tool was something a little less formal. Because here's the twist. Even in this quest for pure logical certainty, mathematicians had to admit that they were relying on their visual, spatial sense of a line, what they called their geometric intuition, to guide them. It was kind of the final piece of the puzzle, and it helped them complete what really seemed to be a perfect, unshakable logical structure. Okay, so the structure seemed complete. From the simple integers all the way to the real number continuum, math was built on what looked like a perfect logical foundation. And then, a crisis hit. A discovery that sent an absolute shockwave through the entire world of logic and reason. This was the bombshell. A guy named Kurt Gödel proved that in any logical system that's powerful enough to describe basic arithmetic, there will always be statements that are true, but that can never be proven to be true from within that system. The dream of a perfect, complete, and provable foundation for all of mathematics was suddenly shattered.
And this intellectual earthquake, it has a date, 1931. Almost overnight, it changed humanity's relationship with the very idea of certainty. This discovery showed that there were absolute, unbreakable limits to what we could ever hope to prove through formal logic alone.
So this forced a huge shift. The goal was no longer some impossible, perfect system. Instead, mathematicians pragmatically rebuilt their universe on new foundations, a set of rules called ZFC set theory, all while accepting that it had built-in limitations. It showed us that mathematics is less of a static set of discovered truths and more of a creative, evolving, very human endeavor. Which leaves us with a final and pretty profound question. We've seen that numbers aren't simple things we just found lying around. They're complex structures we invented, we refined, and we even rebuilt over centuries. So, if they are ultimately a work of the human mind, why are they so ridiculously good at describing the fundamental workings of the universe? Now that is a mystery to think about.